Before you start watching, I should warn you that it may be hard to grasp some moments straight away, so I invite you to pause and ponder anytime you feel you need it. There are also text fragments in the following steps that provide the same content as the video. You may read through them instead of watching the videos if you find that format preferable. As you may know, the name of one of the most famous functional languages, Lisp, is an abbreviation for list processor. Functional languages are known for being really good at working with lists. We may consider lists to be one of the most popular structures in Python as well, so it would be useful to learn some functional features for working with them. Let's create a list of first 10 positive integers. One of the most popular functions to work with iterable structure is map. It takes two arguments, a function of one argument and a list. It returns a list where each element is the result of applying the given function to the corresponding element of the original list. For example, we may get the list of first 10 positive integer squares by mapping the square function onto the nums list. Here you can see map expressed in terms of a list comprehension. Note, it is not actually true that map returns a list. It was so in Python 2, but in Python 3, the map function returns a special map object, which we could turn into a resulting list by applying the list function to it. But if you only need this object to iterate over, don't turn it into a list before that. It is iterable. Only turn it into a list if you need a resulting list. There's a very good reason for returning this map object instead of the resulting list, which is explained in the lesson on laziness. Also, map doesn't really take a list, but an arbitrary iterable, including other special objects like map object. Just like map, all the functions presented later operate on an arbitrary iterable and return a special iterable object, if not a concrete value. But for the brevity's sake, I'll say that they take lists and return lists. That's just a convention. If we use map with a function that takes more than one argument, we can either partially apply this function, or we can just pass map function more than one iterable structure. Then, all the iterables given will be zipped together, and the elements of the resulting tuples will be used as the arguments for the function. For example, here we use map with a function of two arguments. Note that if one iterable is shorter than the others, map will ignore all the redundant elements or the sequences that are longer than the shortest one. Another popular function is filter. Filter takes a predicate. A predicate is a function that returns a boolean value, and a list, and returns a list with only those elements of the original list that satisfy the condition expressed by the predicate. For example, here we filter out all the uneven numbers from our nums list. One more useful function is the accumulate function from the Python's itertools module. It takes a list and an optional parameter, an accumulative function that should be a function of two arguments. If the function is not specified, it's considered to be addition by default. Accumulate returns a list. The way the resulting list is built may be represented like that. Here are examples of using accumulate. Notice this third example where we copy the initial list by using an accumulative function that takes two arguments, but it ignores the first one and returns the second one. Recall this list processing pattern with the usage of listfunc, headfunc, gluefunc, and init value we used before to make a recursive implementation of some common list functions. This pattern is actually very popular and may cover a lot of functions operating on lists you would need. In functional languages, it is called a fold, because we're kind of folding the entire list into the result. In Python, for the same reason, perhaps it's called reduce. Reduce is currently in the functools module, though it was available without importing anything in Python 2. It takes a function of two arguments, a list and an initial value. Then you may think that it inserts the initial value so it is the very first element of the list. Then it takes two leftmost elements of the list and replaces them with the result of applying the given function to them, so after that list is one element shorter. Then it proceeds doing the same thing until there are only two elements left. Then it applies the function to them and the list turns out to be of length 1. The final element is returned as the result of the reduce function. For example, we could express finding the sum of the list as reducing the list with addition as the reducing function and 0 as the initial element. By the way, using reduce is much faster and more efficient in Python than using recursion, but still remains a functional solution. Let's construct another functional factorial computing procedure. For the sake of clarity, we'll make this inst function and this product function that is an analog to the sum of the list, only it counts the product. Then we may define factorial of n as the product of all the positive integers up to n. Another common function for list processing is the zip-width function. Basically, it just takes a function that operates on a tuple. Here it's called the tfunc. Then it returns a function that, given a sequence of lists, will do the following. It will first zip the list to get the list of tuples, and then map this tfunc onto this list. Here's an example of using it. Suppose we want to define a dot product function for two vectors stored as Python lists for the same length. We could define the function straight away like this. Or we can make things more clear and define it as the composition of sum of the list and zip into a list with a multiply function. This multiply function has been defined earlier, and it takes a pair and returns the product of its elements. Let's give another example of using these functions and other functional tools. Suppose we have this text formatted like a CSV file, containing a table with each row except for the header contains information about a person. And we want to make a list of dictionaries where each one represents a person with header elements as keys and the corresponding table values as values. First, we want to make separate functions to split on the semicolon symbol and on the new line character, so we make a partially applied method caller with split method given to it, and then construct split lines and split fields out of resulting functions. Then we split the text we have to get a list of lines. Each of these lines we split in fields to get a list of lists where each list is a row of a table. Then we take the header and the rest of the table separately. Now we wish just to map over the rest of the table and convert each list that is the row of the table into a record. To do that, we need to make a function to map over the list of lists and do the following. It should take each list representing a row, zip the header and the list, and then use a dictionary constructor that turns the resulting list of tuples into a dictionary. Let's check if it works. Well, plenty of useful tools to work with iterable structures may be found in the itertools module. I'm going to quickly review some of them. The chain function is quite simple. It takes a sequence of iterables and makes a chain out of them, kind of like a generalization of the concatenation function. Once again, the result is a special object that may be turned into a list. There are two functions used in list processing, one of which may be easily written based on the chain function, and another one is just a shorthand for commonly used function composition, kind of like zip-with. Concat takes an iterable that consists of iterables and constructs one iterable from these inner ones. Concat_map just maps over an iterable and applies concat to the result. Compress is a function that takes two iterables, one of which is considered to be a mask. That is, it is an iterable containing boolean values. It returns the result of applying this mask to the second given iterable, that is, filtering out all the elements that correspond to the false in the mask. Take while and drop while functions take a predicate and an iterable, and they are only taken or dropping the elements of the iterable while this predicate holds. Star map is like map, except it doesn't take a number of sequences to take arguments for a given function from, but instead it maps over a sequence of tuples, takes each tuple, applies star operator to it, that is, it unpacks it to get whatever is inside the tuple, and then uses unpacked values as arguments for the given function. The result is an original sequence, but instead of tuples there are results of applying this function to elements of each tuple. Here's an example. Instead of this dictionary of quotes, we want to get a list of strings where each string is a quote in the form we define here. Group by takes two arguments, a sequence of elements we wish to group and a feature we want them to be grouped by. This feature function is applied to each element of the sequence. Then for each unique value of this feature function, a group is created. The group by function returns a list of tuples where the first element is the value of the feature function defined in a group, and the second is the list of all the elements of the original sequence that belong to this group in terms of the value of the feature function. Here's an example where we group the so-called meta variable names by their length. Last but not least, the product function. You'll probably want to use the name product for something else, particularly for the product of the list, but you also probably won't like to write the full qualified name itertools.product. This function returns the Cartesian product of the given iterables. That is, given some number of iterables, it returns a list of all the possible tuples, where the first element is from the first iterable, the second one from the second iterable, and so on. There is an optional parameter called repeat, which is set to 1 by default, and it determines how many times do you want to repeat the product you specified. One common usage of the Cartesian product is to reduce the number of nested loops. Suppose you want to get all the possible outcomes of roll and die for 10 times. You could write 10 nested loops or an explicit recursive procedure, but that's not a very fancy solution. Instead, you can get it as a 10th Cartesian power of positive integers 1 to 6. As most of the other functions discussed so far, this cart product returns an iterable object that may be turned into a list if you need that. Let's give another example of using these tools. There's a number of classical problems based on generating and manipulating combinatorial objects. The permutation functions below take some iterable and return all the permutations of its members. There's this help and remove function, which does exactly what remove method of p-vector from persistent model does. It returns a copy of the original list where the first element that's equal to the given one is thrown out. Then we define our function using the following principle. To get all the permutations of 1, 2, 3, we need to get all the permutations of 1 to 3 that start with 1, all the permutations of 1 to 3 that start with 2, etc. But to get all the permutations of 1 to 3 that start with 1 is the same as to get all the permutations of 2 and 3 and append 1 in the beginning of them all. So here's an idea of recursive algorithm. If we had a list of elements, to get all the permutations, we need to take each element and apply the following function to it. Transform it into a list of permutations of all the elements but this one. Then append this element to all these permutations. Resulting structure will be a list of lists of permutations. So we want to flatten it to get simply a list of permutations, which is why after mapping the function we defined earlier, we need to use concat on the result. Finally, we need an edge case. It's reasonable enough to stop once we have one element to make permutations of it, because we know in advance that only possible permutation of one element is the element itself.